In this video, I'm going to talk about a gradient. So gradient is one of the three properties related to the vector field. So if you remember that I talked about before, a vector field actually talks about the field, the vectors that are associated with any point in a given space. For example, if I have a 2D vector field, which means I could actually plot the vector at any point. Basically means I can compute this vector by putting the x and y values. I can compute the v1 and v2 and I can get a vector associated with that point. So for any point I can actually compute a vector associated with that. That's called a vector field. So the vector kind of property, we mentioned three properties I'll talk about in the next few videos. Will include first one is the gradient, the second one is divergence, the third one is the curl. They talk about properties that we talk about the properties related to the scalar field, the vector field. Okay, for the gradient, actually what it talks about is how do I find some of the properties related to the scalar field, and the property is represented by vector. So which means I have a vector field that actually represent the property of the scalar field. I'll talk about what property we mean by gradient. So divergence is a kind of property of a vector field, but we represent that property using scalar. Okay, and curl it's a property for the vector field. We represent property using vector. Okay, so roughly speaking, you can sort of consider that this gradient talks about the fast increase of the scalar field, the direction that gives you fast increase of the scalar field. And divergence talking about how diverged the field is, and the curve represents rotation of the vector field. So I'll talk about it one by one in the next few videos. Okay, so let's start with the gradient. So what is gradient? Since I talk about a gradient is related to the property of the scalar field, so now let's first talk about what is a scalar field. The scalar field is nothing but it's very similar to the vector field. The difference is for every point here, for the vector field, for every point I have a vector associated with a point. For a scalar field, I have a point. For every point I have a scalar value associated with that. That's called a scalar field. For example, if I talk about 2D scalar field, which means it is a field in the 2D space when a scalar value is obtained for any point in the field, so you can find a value. This also applies to a 3D. If we talk about 3D field, a scalar field, which means it is a field in the 3D space when we can assign a scalar value for any point in that field. Okay, now let me give an example about that. For example, if this is Earth, okay, if we want to compute the potential energy for any point in the actual 3D space, so the potential, as we know, is determined by the height, which means how much energy it takes for you to move from the center of the Earth to that point, which is computed by the m, which is the mass of the object, g is the gravitational constant, okay, it's 9.8, h is the height. The height is actually determined by the square root of x squared plus y squared plus z squared. That's the altitude, which is called potential, which is defined by potential energy it takes for us to move from the center of the Earth to the current location. So as you can see, at any point, if I have a point which is x, y, and z, you give me a point, I can actually find the x, y, z, right? Actually, for any point, so I can find a scalar value, right, which is m dot g dot square root of x squared plus y squared plus z squared. It is a scalar, so there's a value associated with it. So this will define a scalar field. You sort of can see it's like this. Okay, if at this point as the center is 0, right, as this one is a value, as you go move up, the value become higher, 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 basically. So that's called the scalar field. The other one example is about the pressure level like below the surface level. For example, suppose this is the ocean, the surface of the ocean, so we know that the pressure level will increase as we move down. It doesn't change if we move left and right, it only moves to the down, and we can have different pressure levels. So which means if I give you x and y and z, so assuming z is my height, how deep it is below the surface of the ocean. So we actually can convert the pressure levels, and this is pressure level at any point underneath the surface of the ocean. Okay, and apparently if you go deeper, your pressure level goes up, so the value will be higher, and this is low. This is relatively high, and this is low, and this is close to the surface, become lower. Okay, if you move this one, so you don't change. Okay, it doesn't change. Okay, so that's roughly you can tell what is the scalar field. So which means at any point you can define a pressure value associated with that point. Okay. All right. So we get a basic idea of what a scalar field is about. Now let's talk about what is a gradient. Okay. So the gradient is defined as this. So gradient is the direction. Okay. Which direction means it's a vector. So this also means it's a vector. To obtain the largest increase of the scalar value in the field at a point. Which means that, hey, if I'm sitting at a certain point, I'm interested in looking at a direction. If I move around a direction, then I'm going to increase the scalar value the most, given a unit distance, right? You're going to increase the fastest, in the fastest pace. That's what it means. Okay? For example, if I'm standing over here, for example, if I could move freely in any direction, okay, which direction will give me the fast increase of my scalar value, which means the potential energy. So if I'm going down, this wouldn't be good, because this will decrease my potential value basically. If it's going here, it doesn't change because your height doesn't change. The best would be I'm going to move away from the center of the Earth. That gives you the fastest increase of my scalar value, which is the potential energy, which means, hey, this will be my gradient. Okay. Similarly for the pressure levels under the surface of the ocean. So if I give a point over here, all right. So I don't want to go up because I'm going up, go close to the surface of the ocean. My pressure will go down. So the best way is going deep down, right over here. It's not good going left and right because it's the same value basically. Okay. Now you get a basic idea what the gradient is about. Okay, so next question will be, okay, how do I compute the gradient? Because I want to figure out what direction I should go to actually try to compute the gradient. Okay, all right. So here I'm going to give you two examples. One is for the 3D scalar field. One is for 2D scalar field. They're really similar. Okay, let's start with the 3D case. So if I give you a 3D scalar field, which is f, x, y, z, which means if I give you a point x, y, z, you should be able to find the scalar associated with that point. Okay, the gradient of the scalar field is computed by, or is given by this. It's really straightforward. It's only just compute a number of partial derivatives. Okay, the gradient, which means the direction that you will increase the scalar value the most or the fastest way, is given by, if you take the gradient partial derivative of the scalar field with respect to x, to y, and to z individually, and then when you put the unit vector along x-axis, unit vector along y-axis, unit vector along z-axis, then you get a vector, right? You basically have a partial f, the original scalar field, with respect to partial of x along the x direction. That's what you would want to go. And also take the partial of f, the original scalar field, with respect to the partial of y along the y direction, y-axis, and then you take the partial derivative of f over the partial of z along the z-axis. Then this vector actually will give the fastest increase of the scalar value at a particular point. Basically, at one point you have this value, right? So at different points, the gradient may be different. May not be the same. For example, if we are right over here, for example, the gradient is this direction. It's not this direction anymore. Similarly, if I'm right over here, let's see, if I'm right over here, the gradient should be going far away from the center, right? So it's sort of opposite of this gradient over here. So which gradient does not necessary to be the same for every point. So as a matter of fact, gradient may be very different for different points in the scalar field. Okay. So similarly for the 2D scalar field, as you can imagine, the gradient is only in 2D space. There's no z component, a k component. You just do the gradients computed by, you take the partial derivative of your scalar field with respect to your x, you time this is unit, this is your along x direction, and partial f xy over partial y along y direction. That's what you have. This is the gradient. Okay, now let's take a look at some examples. How do I compute a gradient for a given scalar field? Okay. Let's say, for example, I give you a scalar field which is fxy is given by 10 times e to the negative x squared plus y squared. So here I'm drawing how the scalar field looks like over here. So what basically you do that is you compute all the possible values at different locations. For example, if I start with x0, y0, I can compute my scalar value is, I just replace xy by 0, 0, okay? It's fxy time is equal to 10 times e to the negative x squared plus y squared. Because x0, y0, so it's negative 0 squared plus 0 squared. So it's 10 times e to the 0. So e to the 0 is 1, so this is 10. So which means, oh yeah, if at 0, 0, I'm getting the value is 10. You simply can compute all the other values differently. So as you can see, this has the highest value, and if you move away from the point, it keeps going down. Okay? Alright. So let's compute a gradient. As I mentioned, the gradient for the 2D space is given by the partial of the original scalar function, the scalar field defined by f. You take the partial f over partial x times I plus partial f over partial y times j, and you have it. So f is already defined given over here, so you just take a derivative. Because this has an exponential, you use a chain rule, which is, if you don't know how to compute this will be the partial f over partial x squared plus partial y squared. So you do have this one is partial f x y over partial x, because this is a little bit complicated. It's the same as partial f x squared plus y squared x y over partial x squared plus y squared, because I know how to, and then you do partial x squared plus y squared over partial x, because this guy, you can see this whole thing as one value, right? It 10 to the e minus x, somehow like that. So it's this guy will be equal to negative 10e minus x squared plus y squared, because you consider x squared plus squared as one variable. You take the derivative with respect to that one, okay? Because you take a partial with respect to that. Because I have negative e to the, it's like partial e to the minus t over partial t. This will be just given you by negative e minus t. So I just replace t by x squared plus y squared. So you replace t by x squared plus y squared. So you basically have this. And then partial x squared plus partial x squared. When you do a partial derivative of x squared plus y squared, y is not a variable of x. So you consider y squared as constant. So partial x squared partial x is 2x. Partial y squared over x is 0, because y squared is not a function of x, right? So that's why you have this. So similarly, you do this partial f x xy over partial y, which is the same as this one. So if you need any help with partial derivatives, you should have known this already. So I will say ask the TA help on how do I compute the partial derivatives. Okay, it's the same as a standard derivative, except that you consider all other variables to be constant when you take a partial derivative with respect to one variable. All other variables will be constant. You can say it's constant. You take the standard derivative. Okay. So similarly, let's give you another example how we do that. Okay. Let's see if I have the. It's a little bit complicated. This is for the 3D vector scalar field. So I have fxy, which is e to the minus x sine y plus e minus x plus z cosine y plus sine z cosine x. Okay, how do I compute the gradient? Alright, so gradient the same way. The only difference, I have 3 variables. So I have to take the partial f over partial x times I plus partial f over partial y times j plus partial f over partial z over k. Okay, so I don't want to talk too much about the details of the partial derivatives. So when I take over this guy, you take complete this stuff over partial x. You consider y and z to be constant when you take the derivative over partial x. Okay, So this will give you this, okay, which basically speaking, you just do, this is a constant, you consider a constant when you take your partial with respect to x. So the first term will be given by this, the second term given by this, the last term given by this term, okay? You keep on computing this part, this is partial f over partial y, okay? This is partial f over partial y. Alright, this is partial f over partial z, okay? So I already computed out for you, okay? So that will be a gradient, which means for any point you compute a gradient, that gives you the direction that will have the highest increase of the scalar value if you move around the direction. Okay? Alright, so this is part 1 for the gradient. I'll talk a little bit more about gradient in the next video.